Let's take a look at example 5.12. We are evaluating an iterated integral over a type 1 region. We're asked to evaluate the double integral over the region D of the function x squared times e to the xy over dA, the area increment. So taking a look at the provided image, we can see that D is this blue triangular region in the domain of the xy plane. And so the first thing that we want to do is take a look at our region and decide how, as a type 1 region, we can define the bounds for x and y. So first, type 1, that's the vertical strips. So I'm going to think about vertical lines that go through the region D. I can start those vertical lines over on the y-axis, and I can keep drawing them until I land at the point 2, 1. Every one of these vertical lines has the top marked along the y equals 1 line. So when we go to think of the region D, we can say that the y value is between the functions. Top function is y equals 1. Bottom function is y equals 1/2 x. Let me write that a little bigger. And maybe not even with blue ink. Let's try white. So y has to be above the 1/2 x line, and it needs to be below the y equals 1 line. And then for our x values, we're going to pick the x values that correspond to the left side of our region, so x equals 0 along that y-axis, and then the right side is defined by this point 2, 1, so the x value there is 2. So we can see that the x values need to range from 0 to 2. And just like in section 5.1, our dA, the area increment, can be written as dx dy or dy dx. And the type of region that you pick is going to determine which of these you use. In the rectangular regions, it did not matter. However, in the general regions, it will. And the reason for that is the y values in a type 1 region are squeezed between functions. So we absolutely need to integrate y first. So for a type 1 region, you will do dy dx every time. And for a type 2 region, you'll do dx dy every time because x will be squeezed between two functions. So when we go to set up our double integral, we know that the function is x squared e to the xy. dA is stuck as dy dx because we're using a type 1 region. The dy is on the inside of our area increment, so the inner integral has the y bounds. We'll go from 1/2 x on the lower bound for y up to 1. And then I'm going to keep the y equals notation so we can remember that those inside integrals are y values. The outside integral is for x values. X goes from 0 to 2. And then from here we just integrate as usual. Now integrating here, we are going to start with that innermost integral with respect to y. So we'll start integrating here. We'll do some scratch work over on the side, integrating from 1/2 x, our y value, up to y equals 1 of x squared e to the xy dy. In this case, y only shows up in the exponent of the exponential term. We will need to do a little baby u sub. Let's let u equal x times y. Then du will be x dy. We happen to have an x, actually an x squared, but one of those x's is going to be absorbed by our du term. So let's look at this instead of x squared e to the xy. We can look at it as x e to the xy x dy. I just split my x squared so that one of them is over here. And the reason I like to look at it this way is because x dy becomes du, and then x times y becomes u. So when we rewrite our integral, it will look like x times e to the u du. And normally, when you do u sub, you would say, hey, you need to pull out all the old variables and replace them with the new variable u. However, you need to remember that in this first integral, x is pretending like it's a constant, y is the variable that we're considering, so this x hanging out along for the ride, not a problem. However, there is one more thing we need to do, which is to change the bounds. The old bounds were for y values, but we just switched our variable over to u, so we need to say, well, what is u going to be if y is 1/2 x? That would turn out to be x squared over 2, so we'll plug in the bottom bound for u is x squared over 2, and then what would have happened if y were equal to 1? Well, then u would be x. So our top bound for u is x. Now we're ready to integrate this. So integrating x times e to the u with respect to u, well, the exponential function doesn't change when we integrate it. So we know that that would be equal to x times e to the u, and then we will evaluate u between the bounds that we've decided we have. So we'll end up with x times e to the x minus e to the x squared over 2. And then we'll plug this back into our original integral, replacing everything in the green brackets with what we've found for that first iteration. So now our integral from x equals 0 up to x equals 2. This time we're integrating x times e to the x minus e to the x squared over 2 with respect to x. And we do see a product of two functions of x. We can kind of simplify this just by distributing that x term. Integrating each one of these one term at a time. This will be a quick little review on our integration techniques. Let's go ahead and separate each term. Since there's no y's left, I'm going to go ahead and drop the x equals on the bounds and just say between 0 and 2 for x times e to the x. And then the second integral is also between 0 and 2, but this is for x e to the x squared over 2 dx. Now that first integral, whoops, too far, x times e to the x, this is going to require integration by parts. Or a memorization of a formula, whichever one works for you. But remember, with integration by parts, you deconstruct your product of two functions as a u function and a dv. We almost always use the polynomial term as the u, and dv would be the exponential e to the x dx. Oops, and that reminds me I lost my dx up there. Then we take the derivative of our u term, which would give us 1 times dx, and then we integrate our dv term, which would give us v equals e to the x. So then the integration by parts says that if you had u dv, that becomes u times v minus the integral of v du. So for us, u is x, v is e to the x, minus the integral of v, which was e to the x, times du, which is dx. That simplifies to x e to the x minus e to the x. So that first integral requires integration by parts. It simplifies to this, which still needs to be evaluated between 0 and 2. The second integral, I'm going to shortcut that one. I'm going to tell you it's u sub, just like we did earlier in the example, and I'll spoil it for you. The u that you should pick is 1/2 x squared, so you would pick the entire exponent of your exponential term. When we integrate that second term and combine it with our first one, we find we have x e to the x minus e to the x minus e to the 1/2 x squared, and we need to evaluate that between 0 and 2. Plugging all of those in, we're plugging 2 in for our first round of x's, so 2 e to the x minus, whoops, I'm leaving an x, which just said that needed to be replaced with a 2. So 2e squared minus e squared minus e to the 1/2 times 2 squared minus the function with 0 plugged in. Now 0 times e to the x is 0. E to the 0 is 1. E to the 1/2 times 0 is also 1, so that's minus another 1. Be careful plugging 0 into with your lower bound. It's really easy to think that plugging in 0 should result in a 0, but remember with exponential terms and trigonometric terms, plugging in 0 does not always result in a 0. So then we clean these up. 2e squared minus e squared, well, that's only 1e squared. And then we have minus e to the 1/2 times 2 squared, that's another e squared, so we have minus e squared here. And then we have minus what's in our parentheses, we have a -2 in there. Our e squareds simplify, we have minus a -2, in other words, a +2. So this double integral over the region D simplifies to the value 2. And this 2 would technically represent a volume. It's the volume above the region D and below the function x squared e to the xy. So 2 cubic units if we're asking about this in context of a volume.